Let's start with the first question. Find the products of these corresponding aldehydes in the presence of sodium hydroxide and water. So let's discuss statement based questions at first and then we'll go for the mechanism here. Whenever you're provided an aldehyde or a ketone in the presence of an alkali, always remember you have to think about aldol or Cannizzaro reaction, the first priority. Because we know this aldehyde and or the ketone, either an aldehyde or the ketone are already well stabilized. They're resonance stabilized here. So in order for a nucleophilic attack to happen here, you can see it is an equilibrium reaction here. This is the first main important thing you have to remember. It is an equilibrium reaction here. Okay. So what kind of reaction will they undergo? They will undergo nucleophilic addition reactions only. All right. In the case of nucleophilic addition reactions to happen, consider if the nucleophile is having a negative charge already. Ma'am, it has a negative charge. So I have an RCHO here. So the nucleophile having a negative charge is available. It goes and attacks this C double bond O and it would happen. But remember, this you will always think about it in the least chances. Always give your importance for the aldol or Cannizzaro types. If the nucleophile is a neutral nucleophile, then what will happen? Like water. Do you think the water will go and directly attack this RCHO? No. So that only you would be provided in an acidic medium here, where the lone pair of electron on the oxygen would first be attacked by the H plus ion. A neutral nucleophile is there. I am having an aldehyde here, and you would have seen they are giving in the presence of H plus, where the lone pair would be attacked. Yes, so that it gets a positive charge, and then the reaction moves on for the neutral nucleophile attack. Remember, all these you can do only in the least chances. Whenever you're having aldehydes and ketone, always give priority for aldol and Cannizzaro reactions here. Is that clear till this?
Yes, ma'am.
Among the aldehydes and ketones, which would undergo this nucleophilic addition reaction to the maximum level, it's obviously the aldehyde, not the ketone. Because ketone is already being provided by the plus I effect, is also sterically hindered. So aldehydes always undergoes a very feasible, favorable nucleophilic addition reactions here. Now, the moment you look at this question, ma'am, I'm having an aldehyde. Check whether they are having alpha hydrogens. This aldehyde is having alpha hydrogen. What about this aldehyde? It is also having alpha hydrogens here. Then that can definitely lead to an aldol condensation product or aldol addition product here. So let us disclose here. Ma'am, CH3, CH2, CHO is there plus CH3, CH2, again a CH2 and a CHO is there. I have told you the shortcut to find the product as well. Hope you remember that, isn't it?
Yes, ma'am.
CH3, CH2, C double bond OH. Now to take up this molecule, CH2, CHO, CH3 it is. So in the presence of heat, what would you do? You just remove this and build up a triple bond there, correct?
Yes, ma'am.
So double bond.
But this is only possible when we heat it, no, ma'am.
When we eat it, yes, correct. If the eating is not just provided, just keep it as H and OH. That's it.
Got it, ma'am. Yes, ma'am.
All right. Now the question is, what is your major product here? There are multiple products possibilities are there, isn't it? Multiple product possibility I could have. I could have go on for my self aldol reaction. Self aldol is also possible here. Yes, crossed aldol is also possible here. Correct, na?
Yes, ma'am.
That this could react with each other to form this product. Possibility is there. Or the another one, CH3, CH2, CH2, CHO. This could react with each other to form the similar kind of product here. Possibility is there. Or as we see just now, This could go for the product formation here. Correct now? Many possibilities are there. Then which will govern my product? The aldol product is generally governed by steric hindrance. This is a major governance here. Steric hindrance. Tell me what is the intermediate you form here? What is
Ma'am,
the intermediate here? Carbon intermediate. What carbon intermediate?
carbanion.
Very good. So definitely it depends upon the carbanion stability as well. So if I'm going to look at this reactant initially, CH3, CH2, CHO in the presence of the alkali, this alpha hydrogen, if it is lost, I'm creating CH minus CHO. In the other case, this was my reactant, isn't it? In the other case, if I reacted with an alkali, what is your carbanion? This is my carbanion, correct? So this carbanion is just given 1 plus I effect, but here I'm able to see a long alkane chain is there to push this plus I effect. So therefore, this is unstable. So this carbanion that is creating the aldol product will be a minor product here. This should be a governing one. All right, ma'am, accepted. If this is governing, either it could undergo a self aldol or it could undergo a cross aldol. Correct? The CH3 CH minus
Yes, ma'am.
CHO would undergo a self aldol, also a cross aldol. Now, among them, which would be the governing product?
Self-aldol, ma'am.
Self aldol. That's right. Very good. Self aldol will be the governing product. Why is that? Because of the steric hindrance. If not, this should go and attack this molecule here, isn't it? Correct now?
Yes, ma'am.
So
Yes.
therefore, your self aldol will be the governing product. So always remember in aldol condensation, carbanion stability is there. Also, in the carbanion stability, steric hindrance is also playing its role. And whenever you are having this intramolecular aldol condensation within the molecule, intramolecular aldol condensation, avoid making more than 6 membered rings. You may have the chance, but don't do it. Clear, ma?
Yes, ma'am.
Yes. So in this question, the question was regarding your aldol condensation here. What are the products that are possible? The very common question here is not just all the products here. The question is about the major product here. So major product, always remember this thing. First, your carbanion stability followed by your steric hindrance. That is very important here. And also remember, if it is a neutral nucleophile, acidic medium always promotes the reaction. Let's go for the next question. It's a statement based question again. The direction mentioned in the reaction is correct. You see that again the ketonic part is being obtained rather than forming an beta hydroxy carbonyl here. Ketone is less reactive towards nucleophilic substitution than aldehyde, and that is the reason. Whether these two statements are correct?
Statement 2 is correct, ma'am.
Okay.
Statement 1, I generally don't know how to.
If you say
Okay.
statement 2 is correct, what do you mean by that? That ketones doesn't like to get attacked by the nucleophile. Correct, na? This
Yes, ma'am. Then
reaction
it's
would
correct,
happen.
ma'am. Both are
Correct.
correct, ma'am.
Correct. Very good. See, only if a nucleophile attack, I would form this product. If not, how will I form the product? So both the statements
Ma'am,
are true
small
here.
doubt, ma'am.
And tell me, pa.
Ma'am, the forward reaction arrow is small, so that means the backward reaction is more favored than forward reaction,
Yes.
ma'am.
Yes.
Got it.
Maybe I would play with this arrow mark also because it's a statement based. We can't go
That's why
because,
I
ma'am.
asked.
Yeah. Just in the arrow mark itself is understood, ma'am. Backward is only favored. We can't just blindfoldedly go with that. We have to analyze. Okay. All right. Go for the next question. What should you do?
Form a carbanion, ma'am.
That's it. Okay. So here I'm having an acetone here. So this is going to have the two hydrogens here. Considering I am the question is to put the heating mark here. So just pull out the two hydrogens along with the water to make up an alkene here. Okay.
Yes, ma'am.
Right. Next question. Is this a intramolecular aldol?
Yes, ma'am. Yes, ma'am.
Yes.
But, ma'am, but
Hmm.
I get confused. Where does the hydrogen get lost? In the position 2 or position
Position 2.
5, ma'am?
Position 5, if you lose it, aren't you making still more small ring? According
Yes,
to your
ma'am.
Bayer strain theory, he knows this is better than this is better than this. So he mentioned till this it's stable. But today we know even more larger rings are also stable.
Yes, ma'am.
Right? So just remove it off along with this and create an alkene. Okay, pa?
Got it, ma'am. Yes.
Yes. Let's discuss about the next reaction. The next reaction is actually in the advanced level. Usually the reaction is called Michael addition reaction. Maybe it has a few fancy names, but the process is very common process here. The moment you see sodium hydroxide is there, it is a base, isn't it? So a base would definitely go and take up an H plus, right? Okay, ma'am. Now I have two possibilities, ma'am. Here also it can go and take an H plus because this is also an acidic hydrogen. Here also it could go and take up, isn't it? So many possibilities of reactions you may have here. Taking a CH2 minus here, the CH2 minus would attack this carbonyl and it would move on. Possibility is there, correct or not?
Yes, ma'am.
Okay. Ma'am, but the product is not provided in the MCQ choices. Then what else we can do? Try it out with this. Here I'm attacking. Okay, ma'am. So here if I attack, if I get a negative charge, again I could go and attack this and I could make up a O minus where it becomes OH. But the product is not available, ma'am. That product is not also not available. Then what else I could do? This is a simple Michael addition where the carbanion is going to attack the olefinic bond here. The carbanion, for example, I'm creating a negative charge here. Okay. So this would go and attack this while this double bond shifts to the alpha position.
Got it, ma'am.
So now I'm having this and this gets a negative charge, double bond and CH3. Okay. All
Yes,
right.
ma'am.
Now, ma'am, this negative is there. Should I go for a double bond formation here? No. Since it's a negative, because it is happening in an aqueous medium, it would take up an H plus, where this would become neutralized. So this possibility of reaction can also happen. And the reaction is called as Michael's reaction. The charge is nullified right now by taking it up the H plus. Protonation step.
Got it, ma'am.
Okay. Right, very good. Let's go for the next question. Before we take up the question, I want you to give me the basicity trend. between aniline, pyridine, and piperidine. Basicity trend. Mithul, Mithul, can you try?
Yes, ma'am. Yes,
Hmm.
ma'am.
Yes.
Uh, Ma'am, piperidine will be the highest, ma'am.
Hmm.
Strongest,
Why?
I mean. Ma'am, pyridine will be
Hmm.
sp2, ma'am.
Okay.
So it will be in the middle.
Okay.
That I know.
Hmm.
Piperidine it will have sp3 if I'm not wrong.
Hmm.
So I think piperidine will be the strongest base, ma'am.
Okay.
Piperidine, pyridine, and aniline. NSP.
Pyridine, and aniline. Very good.
Aniline.
That's the right, correct one here. So piperidine, as Mithul identified, is an sp3 hybridized one here. So this is more basic here. This comes first, followed by here. You can see it is a localized lone pair of electron. It is. So this comes second, while this goes for resonance here. So this comes at the least, right?
Yes, ma'am.
Very good. So if this is a basicity trend, I'm asking you for the second question with the same thing about the C and bond length. Tarun, tell me. C and bond length in
Yes,
the
ma'am.
same three molecules.
And CN bond length in piperidine is the greatest, ma'am.
Okay, piperidine is greatest. Correct.
CN and piperidine, pyridine,
Hmm.
and aniline, ma'am. Because pyridine is sp2 hybridized, so it has a permanent
Hmm.
double bond character, ma'am.
Okay.
And aniline has a partial double bond character,
Okay.
which is still lesser than double bond, ma'am.
Seriously? You're just reversing the order, Ra. Till this, what
One
you said
minute, ma'am.
is right.
Sorry, ma'am.
Ah.
Piperidine,
Hmm.
aniline, and pyridine, because we have
Correct.
an single
Hmm.
bond.
You correct very correctly. You to use the word. It is a partial double bond character due to resonance. So
Yes,
always
ma'am.
remember sp3 will be having higher bond length compared to sp2 compared to sp. Now whenever there is a resonance that is involved, that will involve a partial double bond characters only. But this is not equivalent to the real existing double bond. Natural parent double bond will always be having lower bond length. Okay.
Got it, ma'am.
Yes. Okay. Next question. I'm just writing the numbers here. What reaction? Is this a base?
Yes, ma'am. It's a base,
What is
ma'am.
this molecule?
Um, 1 minute, ma'am.
Hmm.
Sorry, ma'am. Like, I forgot. Uh,
Forgot here, ma'am. Right, forgot.
This is mimicking pyrrole, isn't it? This is pyrrole.
yes, ma'am.
So here there is no double bonds. If I say similar, this is pyridine, and without double bond, you said it's piperidine, then it should be pipirole.
Got it, ma'am. Yes, ma'am.
Okay. So what it would do? You mentioned it's a base. Yes, it's having lone pair. Now what it should do?
It must remove
Hmm.
the most
Ah,
acidic hydrogen, ma'am.
correct. So remove the most acidic hydrogen here. Now the question would arise here, from where would I, because in MCQ choices in JE we will have both the things. From here or from here? From where would you do that?
I'm from the down position, ma'am.
Why?
Ma'am, because like since in the first position, since we have
Hmm.
some alkyl groups like
Hmm.
CH2,
Hmm.
which might
Hmm.
show
Hmm.
like which might give out its electron, ma'am.
Very good, very good. Because the intermediate that you are forming is carbanion. If I'm creating a carbanion, as you mentioned, it would involve in the plus I effect here. But if I create a carbanion here, I am having a carbonyl group here, which will stabilize it, isn't it? So
Yes,
create a
ma'am.
negative, attack, push and push. Then what you will be having? You will be having an OH initially. Now you heat it up. So the dehydration reaction would happen, which will create a alkene here.
Got it, ma'am.
Yes. Let's go for the next reaction.
Ma'am, it forms an alkene, ma'am.
Very good. It forms an alkene. Super.
A most substituted alkene, but only one alkene is possible if we remove hydrogen from any carbon.
Hmm. Hmm. Look at this. As you mentioned here, the question is asking you find the product and draw the reaction coordinate for the given reaction here. All right. As you said, if it's going to form an alkene, who is the leaving group there?
Chlorine, ma'am.
Chlorine. Where is chlorine there? This question draws seventh one.
Oh, sorry, ma'am. I did eighth one.
Okay. The Smith will give a try. What is the leaving group here?
Hydrogen, ma'am, because the strong base.
Do you consider hydrogen as a leaving group?
Sorry, ma'am, sir.
Ah,
Ma'am,
Ma'am,
but
can I come back in a minute, ma'am?
hmm. So you find there is no leaving group at all here. Can I say that?
yes, ma'am.
What about OH?
No, ma'am, it can't, ma'am, because we don't have an acid.
That means can I say it's a poor leaving group?
Yes, ma'am.
Just like fluorine. It's a poor leaving group. Shall I say that?
Yes, ma'am. We
Yeah.
can say.
So whenever you are having a poor leaving group and a strong base is provided, what is the elimination method called as? Even CB,
Yes, ma'am. Yes, ma'am.
right? So we have learnt about, we will revise and then we'll start with it. We have learnt about different types of elimination reactions, E1, E2, E1 CB elimination reactions. So when I said it's even elimination reaction, it goes with carbonium formation. E2, it goes with, does it form any intermediate?
No
No carbon,
intermediate, ma'am.
no carbon intermediate would be here. Here the intermediate is carbanion. Even needs sterically plus I groups hindering should be there. Here no steric hindrance. Correct? What kind of a base? Not much influence or affected by the base strength here. It's not that much affected by the strength of base. Here it needs strong base, it needs, and a better leaving group is a must for both, isn't it? Both
Yes,
of
ma'am.
them needs a better leaving group here. There is one thing specific about the E2 mechanism is that it definitely needs a hydrogen to be anti to the leaving group, isn't it? Here no stereochemistry specific is there. What about even CB? Poor leaving group. That is the mandatory condition here. Like F minus, like OH minus. Poor leaving group it will be. Shall we say that?
Yes, ma'am.
No stereochemistry. There is no stereochemistry specificity is there. No, nothing is there. Even what is your rate determining step? The rate
Ma'am,
determining step.
carbanion
Ah,
formation, ma'am.
very good. Carbonium formation is the rate determining step here. Here, no such steps. It's a one single step transition it's happening, isn't it? What about here?
Yes, ma'am.
In even CB?
Carbanion, ma'am.
No. Leaving group departure is your rate determining step.
Got
That
it,
is
ma'am.
your RDS. Okay, ma?
Yes, ma'am. Got it.
Right. So having this in mind, let us practice the question. So right now I am able to see that it is having a poor leaving group. OH minus is there. I am having a stronger base. And very important thing about the even CB, one more thing is that as I said, the intermediate is a carbanion. Try to make this carbanion stable. That is very important. Okay, so what shall we do at first? Eliminate this H plus so that you create a negative charge here and OH is there. Now push and push. That's it. Okay, ma?
Got it, ma'am. Yes, ma'am.
All right. So the mechanism is even CB. Now we have to draw the reaction coordinate. So as we mentioned, formation of the second, this one is your RDS, isn't it? So the first one would be having a lower energy. Which one? Formation of negative charge, carbanion. But the second one, where I am going to depart the leaving group removal, will have the higher energy. So this is my energy profile type.
Got it, ma'am. Yes, ma'am.
Yes. Go for the next question. Same type of question. Find the product, draw the reaction coordinate. And also remember here the carbanion is stable because I'm having a carbonyl here. So if you are having two possibilities, ma'am, I can remove an H from this side as well as that side as well as check from where you would remove it. Okay,
Got it. Yes, ma'am. State reaction on alkene, ma'am.
very good,
Elimination. Yes, ma'am.
very good. Elimination. What elimination?
E2 elimination, ma'am.
Think well. Is this a sterically strained plus I effect molecule?
Yes, ma'am. Yes, ma'am.
Then Why E2?
Then sorry, ma'am. It's even, ma'am.
It's even. The moment I see a conjugate base in the presence of its salt or in the presence of an acid, alcohol, it's a base. Now I could see this is a tertiary alkyl halide, isn't it? So therefore, from here the H would have, I could, as you are having this confusion between E1 and E2, so what would be the first step here? Removal of this chloride ion. The removal of this chloride ion would form me a tertiary carbonium ion. Now forms an alkene. Can you say that?
Got it, ma'am. Yes, ma'am.
So it is even elimination method. Okay. What about the reaction profile? What is the RDS?
Carbocation is the
Formation
RDS.
is
Then, ma'am.
RDS. So this would be more followed by this. This is carbocation. This is alkene formation.
Yes, ma'am.
Okay, next.
Ma'am, here
Hmm.
both E1 and E2 are possible, no, ma'am.
Yes, both are possible here. That's correct.
Then which one should we like take when they have given options E1 or E2 like that, ma'am?
See, you're making it to think about the E1 or E2 because it's a secondary alkyl halide. I have two possibilities here. But what about a base? What kind of a base it is?
Strong
It's a
base, ma'am.
strong base, then go for E2.
Got it, ma'am. Yes, ma'am.
Understood, ma?
Yes, ma'am. Got it, ma'am.
So for E2, it's only a one single plateau here. Next. Yes. So you're having a RO minus here. Here it is going to be lithium diisopropyl oxide here, LDA. Very bulky base it is. We have always learnt about this tertiary butoxide, which is a bulky base, isn't it? So
Yes, ma'am.
whenever it is a bulky base, what kind of an elimination reaction will be there? Whether it will go for Hoffman product or an Seitzov product.
Ma'am, um, 1 minute, ma'am.
Hmm.
Hoffman product, ma'am.
Very good. Whenever you are having a bulky base, lithium diisopropylamide or your tertiary butoxide, bulky bases, go for Hoffman product here, which is nothing but less substituted alkene. So that means I would form an alkene here where I could remove this H plus where it is going to form a less substituted alkene. Can I say that?
Yes, ma'am.
What about RO minus then? It is not a bulky base. So I could go for alkene formation in this side.
Got it, ma'am. Yes, ma'am.
Yes.
Alkene
Ah,
formation on that side would be more saturated. Okay, ma'am. Got it.
correct only, da. 2 or.
Yes, ma'am. Should we solve 11th or 12th, ma'am?
11th. Ra.
Can you do this problem, ma'am?
This reaction is an example of Diels-Alder reaction, where you will have dienes and dienophiles. Okay, this is your diene here. So they will generally be giving you a double bonded systems here. For example, the very common example is cyclobutadiene with your ethylene here. The reaction is generally either photo-activated or heat-activated. Okay, so it's a kind of a free radical kind of reaction. Like this it happens. This is your product. It's a cyclic addition here. The reaction is also called a cyclic addition, also called as 4 plus 2 cyclic addition. This is 4 electron and this is 2 electron, 2 pi electrons. 4 plus 2 cyclic addition.
Got it, ma'am.
Now here you are provided with benzene. Same logic. Keep pushing the bonds so that you just club them up like this. Okay, that's it.
Yes, ma'am.
Understood, what?
First
Hmm.
statement is false, ma'am.
This is false. Why do you say that?
No, because it's single bond, and
The,
in benzene we have.
don't you have delocalizations here? Possibility is there.
Yes, ma'am.
Whenever you are having conjugation, whenever there is a possibility of conjugation, try it. Ma'am, in benzene also the same thing will happen, ma'am. Isn't it? Correct or
Yes,
not?
ma'am. Yes,
Then
ma'am.
why do you say it is going to be true over here? If it is benzene also,
Here, triple bond can also come.
exactly. Extra electron density cloud is there. So which emphasizes it much more.
Yes, ma'am. I didn't think it in that way.
Okay. Then the next one. The bond length in of BC is longer than the triple bond in ethane. True or false? Obviously, it has to be true,
Yes, ma'am.
na?
It's
Again,
true, ma'am. It's true, ma'am.
again it is involving in resonance. In ethane, there is no resonance. So again, it's true only. Let's go for the next question. Mithul is here?
Yes, ma'am. He's there, ma'am.
Okay.
Yes, ma'am. Yes, ma'am. I was here, ma'am.
Ma'am, I
Hmm.
guess like we have to use delta G is equal to minus RT ln K
Okay.
and find the temperature, ma'am.
Okay.
And then should we
What will you
use,
do with temperature, right?
ma'am, but
Temperature is already there, pa. Why do you need to find out temperature?
okay, ma'am. Then how can we find the initial pressure, ma'am? Because by obtaining it, we can directly find the alpha value, ma'am.
So as you say, delta G naught is equal to minus RT ln Kp. Calculate your Kp value. Hmm? They're asking for degree of dissociation of water. That is alpha here. How do you write Kp? Kp is partial pressure of hydrogen, partial pressure of oxygen power off divided by partial pressure of water. As you said, ma'am, that I don't know anything about the pressures here. Then, but your total equilibrium pressure is there. Whenever the questioner is giving you about total equilibrium pressure, remember you have to use mole fraction multiplied by total pressure for partial pressure. Our partial pressure is nothing but mole fraction multiplied total pressure, isn't it? You
Yes,
get
ma'am.
me?
Yes, ma'am.
So that means it is 1 minus alpha. This is alpha and this is alpha by 2. So then calculate the partial pressure here. For hydrogen, how much it is? Alpha divided by 1 minus alpha plus alpha by 2.
Got it, ma'am. Yes,
Yeah,
ma'am.
same thing here. The whole divided by here it is 1 minus alpha plus 1 minus alpha plus alpha plus alpha by 2. So here you will be having 1 plus alpha by 2 power of 1 plus alpha by 2 power of, correct?
Yes, ma'am.
Yes. Go on then. Same logic here. So you'll be having 1 minus alpha at the numerator, 1 plus alpha by 2 here, the denominator. So what is the clue here? Always, whenever you are provided the statement with equilibrium pressure, this much is the equilibrium pressure, then definitely there should be the equation which relates partial pressure to the total pressure.
Got it, ma'am. Yes, ma'am.
I hope you can work it out later. Okay.
Yes, ma'am. Because we can
Yes.
eliminate 1 minus alpha as 1.
Exactly. So alpha is negligible to 1. So everywhere I can just eliminate it. That means I don't have my denominator part at all. That's your understanding here. Here also I can eliminate it. Can I say
Yes,
that?
ma'am. Yes,
Yeah.
ma'am.
So get your KP value here. So that you could go for alpha by 2 power 3 by 2 because it's alpha power 1. From there you can calculate alpha. Okay.
Got it, ma'am. Yes,
Right.
ma'am.
Waiting for the next question. Nucleophilic substitution reactions, SN2 AR type of reactions. So in the last class and all, I was just sending you the photos, pictures of this kind of reactions. So usually no SN2 and sp2 accepted, but whenever I'm having a strong base or when I'm having too much of electron withdrawing groups, definitely the reaction would happen,
Yes, ma'am.
right? So we discussed about two things here. If I'm having benzene and an halogen is there, which is a leaving group, okay, and where there is an electron withdrawing, let me say NO2 is there. A common nucleophile can also go for a reaction here, where it would just go on for the reaction, where this X would be getting substituted by the nucleophile. Here. Possibility is there. And this complex, what you see is called as Meitner complex. In the electrophilic aromatic substitution, you say sigma positive complex, na? And this will be called as sigma negative complex.
Got it, ma'am. Yes, ma'am.
All right. So here also the same thing is happening. Three electron withdrawing groups are there. So what you're going to form here is a Meitner complex here. So this methoxide is never a leaving group here. Very not that much facile leaving group like halogen, but it is a leaving group. They are done in ester reactions and all. Methoxide generally leaves when the Grignard attacks the carbonyl, isn't it?
Yes, ma'am.
Where you have OC2H5 now, and you will be having NO2s here. There is no benzene formation here. When will a benzene formation happen? When your base is typically sodamide, then the benzene formation happens.
Got it, ma'am. Yes, ma'am.
Okay, next question.
Ma'am, B and D is correct, ma'am.
Okay. What
Ma'am,
about A?
Uh, A is false, ma'am. I think it's
Correct. A is true. The statement is just from your NCRT. See, if it's an open container, why do you think the reaction should come to the reverse way? It should always go to the forward way only, na?
yes, ma'am.
So equilibrium is possible only in a closed container. That's correct. That's true. And both the opposing forces occur at the same rate. That is also true here. When equilibrium is attained at a given temperature, the value of all its parameters become equal. Is this correct? Look at the word becomes equal. That means when I say A is in equilibrium with B, they say it should be also zero point 0.5 moles. It should be also zero point
No,
0.5
ma'am.
moles. No, so this is false. This is true.
True.
For dissolution of solids and liquids, solubility is constant at a given temperature. That's correct.
Got it, ma'am.
What is your major product?
Ma'am, like just now you said it's benzene formation.
Yes, very good. So initially, if they are giving just 1 mole, it would deal with benzene formation. If they said excess, that means NH2 minus is still available. Now this NH2 minus will attack as a nucleophile attack here. Now the question is, would it attack from here? So the bond shifts like this, or would it attack from here so that the bond shifts like this? What is the correct way?
I guess the first one, ma'am, like on the left side.
This one,
Ah, no, ma'am, left side.
this one. Correct,
Yes,
very
ma'am.
good. Why is that?
Because CF3 is a strong electron withdrawing
Hmm.
group, ma'am.
Hmm.
It
Correct.
creates an electron deficiency,
Hmm.
so it can easily pull its electron.
Yes. So if I am going to push it, I create a negative charge here, which will be stabilized by this CF3. Now H plus would attack this so that they get electrically nullified.
Yes, ma'am.
Okay. So in this class, we have discussed about aldol condensation reactions, their importance, their stabilizing factors here, intramolecular aldol, Michael addition reaction, basicity orders, and the carbon nitrogen bond length orders, and even E2 even CV mechanisms, followed by Diels-Alder and chemical equilibrium as hint to know where would I, which equation should I mandatorily use here. Okay, so keep working.
Yes, ma'am.
Let me know if in specific any chapter that you want me to revise or redo the questions on it. Please let me know for our next session.
Yes, ma'am. Got it.
Okay,
Yes, ma'am.
okay, bye bye.
Thank you, ma'am.